So example 1 says a particle is moving along the x-axis with a position function x of t equal to 1/3 t cubed minus 4t plus 5. Find the velocity and acceleration and describe the motion of the particle for t greater than or equal to 0. So they give me the position function and I need to get the velocity. So I'm going to take the derivative. V of t would be t squared minus 4. And if I'm going to describe the motion of the particle, I need to find where the particle changes directions, which is where the velocity is equal to 0. So I'm going to take my velocity equation, set it equal to 0. That gives me t squared is equal to 4. So t is equal to technically plus or minus 2, but we're talking about time, so I don't have negative time. So I know that it's probably going to change directions at 2. I'm going to make a little sign chart of the velocity graph and check on either side of 2. So if I plug in 0 to the velocity, this will be negative. And if I plug in 3, I get 9 minus 4, which is positive. So here's my sign chart for the velocity equation. And also I'm going to find the acceleration equation, which would just be 2t. And if I set this equal to 0, I get t is equal to 0. And so if I make a graph of the acceleration, which starts at 0, and I plug in a positive number, this will be positive. And so the reason that I did the sign chart for the velocity and the acceleration is that so I can describe the motion of the particle. So I'm going to say the particle begins at position 5. How do I know this? How do we get the initial position? If I plug 0 in for t, I get 0 minus 0 plus 5. So it's going to begin at position 5 and moves which direction? And moves, well, third period is on their calculus game today. It moves to the left. How do I know it moves to the left? The velocity is negative for the first 2 seconds. Okay, so it moves to the left for 2 seconds, then moves right indefinitely. Using the signs on my velocity graph. And now I'm going to talk about when the particle is speeding up or slowing down. And so if you will remember when we talked about this in chapter 3, if the velocity and the acceleration have the same signs, then the particle, either both negative or both positive, then the particle is speeding up. And if they have opposite signs, then the particle is slowing down. So I can say the velocity is negative from 0 to 2 and the acceleration is positive. So the particle is slowing down from 0 to 2. And it's going to be speeding up from 2 to infinity because my velocity is positive and my acceleration is always positive. So it's speeding up from 2 to infinity.
Why didn't you do the left side for the acceleration sign chart?
It's not defined past 0 because time has to be greater than or equal to 0. Okay. Let's look at what we call the second derivative test for local extrema.
So is the acceleration always positive?
In this case, yes, because my derivative for the acceleration is 2t, and time has to be positive. Therefore, the acceleration is always going to be positive in this case, right? All right, so my second derivative test for local extrema. So this is one of those things that it makes sense, and we've already seen it, but this is just formalizing it in a theorem. It says, if I have some point, and at that point there is a horizontal tangent. Okay, so I'm going to draw a point, and this says my derivative is equal to 0 at that point. So I have a horizontal tangent. And my second derivative is negative, meaning that my function is concave down. So if I have a horizontal tangent and the function is concave down, then my second derivative test says that this has to be a maximum. It has to be because it's a horizontal tangent and the function is concave down. And likewise, if I have a point and I have a horizontal tangent, but this time my second derivative is positive and my function is therefore concave up, then this point has to be a minimum. So let's look at this example. I believe this was taken from a previous AP exam. It says if f of 7 is equal to 2 and f prime of 7 is equal to 0 and f double prime of x is less than 0 for all x, then which of the following cannot be the value for f of 8? So let's make a little sketch. If x is 7, then y is equal to 2. 1, 2, 3, 4, 5, 6, 7. So I've got a point right there. This says that I have a horizontal tangent at 7. And this says that my second derivative is negative, meaning for all x values, meaning that my function is always concave down. So it looks something like that. So if this is the case, my theorem says that 2 has to be what? It has to be the max. So if 2 is my max, the function cannot equal 3. It could equal 1 or 0 or negative 7, but at f of 8, it cannot be 3. In other words, if I went out to 3 and went up to this point right here, I could not have this point defined because my second derivative test for local extrema says that the maximum has to be here at the horizontal tangent. All right, well, let's do a little multiple choice practice. So this says the graph of f prime of x is shown in the figure. Which of the following must be true about the graph of f at x is equal to 3? First, label your graph. This is f prime. And so then they are going to ask questions about what is going on at x is equal to 3. And scanning the answer choices here, they're asking about decreasing or increasing and concave up or concave down. So I know that at 3, f prime is increasing at x is equal to 3 because f prime of x is positive. Okay, so looking at this, this is a graph of the first derivative. It is above the x-axis at 3. Therefore, my derivative is positive. Therefore, my original function, Sorry. That should say f is increasing. F is increasing at x is equal to 3 because f prime is positive. Okay, it is above the x-axis. I also know that f double prime is, okay, so how do I get the second derivative from the first derivative? From a graph. I'm looking at the slope, right? If I have the first derivative and I want the second derivative, I need to look at the slope because the derivative is the slope. So looking at this point, do I have a positive slope or a negative slope at 3? It's a negative slope, right? Therefore, f double prime is negative at x is equal to 3. Look at the slope, which implies that f is concave down. Okay, so since I have a positive derivative, it's above the x-axis on the f prime graph, and I have a negative slope at 3, implying that my original function is concave down, the correct answer here is C, f is increasing and concave down.
Could you also look for it across this x? Like if you did it as it was decreasing or increasing, and then it was decreasing, so that means
That you would find an extrema wherever this graph crosses the x-axis.
so
Because my derivative would be 0, and then, for example, this is going to be a maximum on the original graph because my derivative is 0 and it's increasing, then it's decreasing.
yeah, so could that tell you that it's concave down also?
That in and of itself, no. You would get the concavity from the slope of this graph. Take a look at the next 2 questions for me and see if you can answer them. Go ahead and do that for me right now. So why don't you collaborate with your friendly calculus neighbor there and see how he or she is doing? And if they are stuck, see if you can help them out. All right, here we go. Let's take a look at this. Let f of x be a function defined on the interval from -3 to 5. The graph of the derivative of f of x is shown below. So this is f prime of x. I'm going to label it because I get confused sometimes. So this is f prime of x. Which of the following statements must be true? The graph of f of x is increasing on the intervals from -3 to 0 and 2 to 5. Is this true or false? Well, why is it true? Because this is the graph of the derivative, and it is above the x-axis on those intervals. Therefore, it is positive. Therefore, the graph of my original function f would be increasing on those intervals. Number 2. The instantaneous rate of change of f at x is equal to 0 is 0. True? False? Too bad they can't see that on the video, right? This is also true because what is my derivative at 0? Since this is a graph of the derivative, I'm just going to look at what happens at 0, and it crosses the origin. Therefore, it is equal to 0. Part 3. The graph of f of x is concave up on the interval from 2 to 5. So for this to be true, I would have to have a positive slope from 2 to 5. And I do not have a positive slope. I have a negative slope. Therefore, this is not true. Therefore, the correct answer here is C, 1 and 2 only. And part C. The graph of f prime of x is shown below. Use the graph of f prime of x to approximate the intervals on which the graph of f of x is concave up. So again, this is f prime of x, and I want to know about the concavity. So I'm looking at the slope, and I want to know where it's concave up. So I need to have a positive slope on this graph. So that is going to be, let's see, from 0 to 2 and 4 to 6. Approximately, it will have a positive slope. Therefore, it's concave up. Okay, so questions over anything so far? Anything that I can clarify for you?
The A question of what we just did you say it crosses the origin, or is it just because it is 0 at that point?
It's 0 at that point.
Okay.
All right, here we go. Example 4, given the graph of h prime of x. So I'm going to label this. This is h prime of x. Estimate the intervals on which the function h is increasing and decreasing. Okay, so I'm going to say h is increasing when my derivative, h prime of x, is positive. So looking at this graph of h prime of x, it will be positive whenever it is above the x-axis. So I'm going to say from -3 to -2. And then from 0 to 3. H is decreasing when h prime of x is negative, and it's going to be negative whenever my derivative graph is negative. And so therefore I'm looking at when it is below the x-axis. So from -2 to 0. All good? Part B says estimate any local extreme values of the function h and where they occur. So I'm looking for extrema. Extrema can occur at 1 at critical points or 2 at endpoints. So critical points are where the derivative is 0 or undefined. So let's start there. I can say that x is equal to -2. At x is equal to -2, it is a maximum. Because, why is this a maximum? My derivative, h prime of x, equals 0 and changes from positive to negative. So because this derivative graph is increasing and then after that it is decreasing, it must be a maximum. Okay, next up is x is equal to 0. And I know that x is equal to 0 is a minimum. Why is it a minimum? Because look up here. We said that it was decreasing from -2 to 0, and then it is increasing from 0 to 3. So it was going down, and then when it gets to 0, it goes back up. So x is equal to 0 is a minimum because h prime of x is undefined. How do I know it's undefined? There's a jump discontinuity on my derivative graph. So it is undefined and changes from negative to positive. It's below the x-axis, then it's above the x-axis on the derivative graph. X is equal to 1. There is no extrema. Why not? The derivative does not change signs. And also, if you look up here, we said that it was increasing on the interval from 0 to 3. So if it's increasing the whole time on that interval from 0 to 3, I can't have an extrema in the middle there. Oh, wait, I'm not done because I need to check those stupid little endpoints, right? Because I can also have an extrema at the endpoints. So I got x is equal to -3. And at x is equal to -3, it is a what? It is a minimum. How do we know? Because h prime is positive just after the endpoint. And now I'm going to check my other endpoint, which is x is equal to 3. And x is equal to 3 is a maximum because h prime is positive just before the endpoint. So it is increasing, and then it stops. Therefore, it must be a relative max. All right, well, I think it's a bit time for a stretch break. So stand up, stand up, stand up. Oh, oh, oh. Whew. All righty, here we go. A function is continuous, so I know that it will be a continuous function on the interval from -4 to 2. However, we have the discontinuous function g prime with a domain from -4 to 0 and 0 to 2, and it's shown in the graph at the right. And part A says find the x coordinates of all local extrema of g. So this, I'm going to label, this is g prime. I'm going to find the extrema, which is also what I just did. However, I'm going to add something in on this problem, which part B says we're going to sketch a possible graph of the original function g. So the first thing we need to do is to find our extrema. We're going to start with the critical points. So where my derivative is 0. And so there is an extrema at x is equal to -3. I know that it is a maximum because g prime equals 0 and changes from positive to negative. And so then I'm going to go to the next one, which is x is equal to -1. And I know that this is a minimum because g prime equals 0 and changes from negative to positive. And now I'm going to go to my next one, which is x is equal to, what's the next one? It's 0. X is equal to 0. And what is x is equal to 0? How do we know it is a max? Because g prime is undefined and changes from positive to negative. Now I'm going to check those little endpoints. So I got x equals -4. And that is going to be a minimum because g prime is positive just after the endpoint. And finally, I have x is equal to 2, and that is going to be a minimum because g prime is negative just before the endpoint. And so now part B says sketch a possible graph of g. So I know that I must draw a continuous function. There are no holes in that or asymptotes in my original function. It's going from -4 to 2. I know that at -4, I have a minimum. And I know that at -3, I have a maximum. I am. You can't tell how high or low the y coordinates are based on the information that they give us. Okay. I just know that they're a relative max or a relative min. At -1, I have a minimum. So it's going to go down here. Then it's going to go back up at 0 because it's a max. And at 2, it's also going to be a minimum. The other thing I need to pay attention to is whether the derivative at my extrema is equal to 0 or undefined, because that will determine if I have a horizontal tangent, if it's equal to 0, or if it's a cusp or a corner where my derivative is undefined, and my derivative is undefined at 0. So I need a cusp or a corner there. So let's see, this is going to go up and then down and then up to the corner there and then down. I have a corner at x is equal to 0 because my derivative is undefined. I know it's undefined because I have a jump discontinuity in my derivative graph. I'm going to check everything. I've got a relative minimum at -4. It goes up. At -3, I have a max, and my derivative is 0. At -1, I have a min, and my derivative is 0. Not differentiable at 0. And then a relative minimum at 2. And so everything checks. Okay. So questions on that one. We're going to do one more of these with a little bit more detail. So let me answer any questions first before we go on to the next one. Is everybody? okay with this one or have any questions? Yes.
When you were doing the extremo, like how do you know, like, I know like the -3 and -1 since it crosses, but why is the 0?
Okay, because at 0, what is happening right here? Is it increasing or decreasing? It's increasing because my derivative graph is above the x-axis. And then what happens after 0? It is decreasing because it is below the x-axis. So it's increasing and then decreasing. Therefore, it has to be a maximum here. And I know that it's going to be a corner because there's a jump discontinuity here. Okay. All right. Here we go. Finding f from f prime and f double prime. A function f is continuous on its domain of -2 to 4. And then they give me some information, and then they give me a chart. And number 1 says, find where all absolute extrema occur. Okay, so to find the absolute extrema, I need to check the critical points and the endpoints. So a critical point is where the first derivative is 0 or undefined. And so I'm going to look first of all at x is equal to 0 because my chart says that the first derivative does not exist, so it is undefined. Is there a sign change? On the left side of 0, it is positive, and on the right side, it is negative. Therefore, x is equal to 0 is a max. Because f prime equals 0 and changes from positive to negative. The next place I'm going to check is at 2, because x is equal to 2, at x is equal to 2, my first derivative is 0. However, this is not a max or a min, because why is it not an extrema? There is no sign change. Negative, negative. Okay, so those are the only critical points. Yes? I don't. You can go. Those are the only critical points. I still need to check my endpoints, though. So I'm going to check at -2. X is equal to -2 is going to be a minimum because f prime is positive just after the endpoint. And I know it's positive because I'm looking at the first derivative there. And then I'm checking x is equal to 4 is the other endpoint. And over here, my first derivative is negative until it gets to 4. So this will be a minimum because f prime is negative just before the endpoint. Okay, so that is the first one, the extrema. Part 2 says find where the points of inflection occur. And so how do I do that? I don't have a graph because that's what I'm going to sketch. So a point of inflection is where the concavity changes. But how do I tell that from just this information? It's where the second derivative is 0 or undefined. And there also has to be a sign change. So for example, at x is equal to 0, the second derivative is undefined. However, it is not a point of inflection because I've got plus and plus, it's concave up and concave up. So there's no sign change. At x is equal to 2, however, there is a point of inflection. X equals 2 is a point of inflection because f double prime equals 0 and changes from positive to negative. So now I need to sketch my graph based on the information that they give me. And so I'm always going to start at the points. I know that when x is -2, y is 5. So I'm going to put a point there. And when x is 4, y is 1. So I'm going to put a point there. So at -2, I have a minimum. So it's got to go up from this point. Also, now I'm going to look at the first derivative and the second derivative. So my first derivative from -2 to 0 is positive, and my second derivative is also positive. That means it has to be increasing, number one, and then it has to be concave up. So it's going to do something like this. It's going to go up, and it's going to be concave up. And I know at 0, I have a maximum. And I also know that at x is equal to 0, the first derivative does not exist. Therefore, I will have a cusp or a corner at x is equal to 0. And then I'm going to look at the interval from 0 to 2. My first derivative is negative, so my function will be decreasing. And it is also positive for the second derivative, so it will be concave up. So this is going to go down, but be concave up until we get to 2. And at 2, I wrote here that there was a point of inflection. So it's got to switch concavity at x is equal to 2. And if you will look on this interval from 2 to 4, the first derivative is negative, so it's going to be decreasing. However, it's going to be concave down on that interval, so it will do something like that, where there is a point of inflection there at x is equal to 2. And so then if I were to go back and check all of these, are those points defined? Is it increasing and decreasing where it should be? Is there a max and min wherever it should be? Is my derivative undefined, for example, at x is equal to 0? All of those should check off.
On x equals 0, how do you know what value y value to go to?
You do not know that y value. So this graph could be shifted up or down a little bit, but you don't know that. You know there's got to be a cusp or a corner there, but and that it's a relative maximum, but that's it. All right, I need you to try the last 2 multiple choice problems right now, and then we will call it a day. So work on those right now, please. Why don't you collaborate with your friendly calculus neighbor there? See if we can figure these out.
It's a corner, but it's on the
Oh, I thought it was asking about. Oh, yeah. Did you say that number 3 work?
Yeah, because it's the graph of the derivative.
But it's asking about
But then,
okay, so like,
no, you. I didn't put that.
how do you know something's not? It would be like
If there were like a whole.
yeah, it'd be like this one.
Right here. Wait.
All right. The graph of h prime of x is shown. So this is h prime of x. Which of the following statements must be true about the original function h of x at x is equal to c? Okay, I'm going to eliminate the second one there immediately because the original function is not increasing at c because on the graph of the derivative, c is below the x-axis. So therefore it must be decreasing. Let's look at 3. Is there a derivative at c? In other words, is this point defined? Yes, it is. Therefore, it is differentiable. If they had asked, is h prime of x differentiable? That would not be true because there's a cusp or a corner there. But if there is a point here at this point, then there is a derivative in the original graph. And if there is a derivative, that means it also must be continuous. Therefore, E is the correct answer, 1 and 3 only. And finally, the graph of the derivative of f of x is shown above. So this is f prime of x. Which of the following statements must be true? F of x has a maximum at x is equal to c. No, the derivative is not equal to 0. F of x has a maximum at x is equal to d. This is true. The derivative is 0, and it changes from positive to negative. And f of x is decreasing at x is equal to e. This is also true. My derivative graph is below the x-axis. Correct answer is E as well.